So today we're going to get into some stuff where you could do problems and calculations. We're going to start out with units and unit conversion. So the basic idea of this is any scientific measurement has units. And all units that we use in this class can be made up of a combination of three simple unit types. When you get into physics 2, there'll be other ones. Charge is one. When you get into atomic stuff, there's some other one. But in this class, all units can be expressed as a combination of three simple types. Those are length, and the SI units for length, the Standard International or System International or something, is meters. Time, and the SI units for time are seconds. And mass. And the SI units for mass are kilograms. You'd think maybe grams because you don't have the prefix on it, but it's kilograms. And so the way that works is like, well, what about, so how do you measure speed, say, for, as an example? Well, that's a combination of meters and seconds, length and time. That you can write that as miles per hour, meters per second, that kind of thing. And every unit that we're going to use in this class can be expressed as some combination of these three simple types. How many people have had a class where you've done unit conversions? Probably chemistry, almost everybody. And maybe everybody, and some people's arms are tired. All right, well, so unit conversion, the idea is just like this. Like a lot of these you're used to doing just in your head, even without like a formal approach. So for example, how many inches are there in 3.5 feet? And to do that, we're going to use the fact that 1 foot is equal to 12 inches. And by the way, these are non-SI units of length. Okay. Well, intuitively in your head, you know that the answer is you just multiply that 3.5 by 12, and that gives you the number of inches. But the way that works is, think of this ratio um, 1 foot over 12 inches, and 12 inches over 1 foot as, a ratio of equivalent quantities. and therefore they're equal to 1. And what that means is that you can multiply anything by either one of these ratios without changing the thing that you started with. It'll look different, but it'll still be the same thing, okay? Because you're dividing it and multiplying it by the same quantity. So we're going to take that 3.5 feet, that's our starting value, and we're going to multiply it by one of these ratios, okay? And that's going to change the units without changing the actual thing that it represents, okay? So 3.5 feet. We're going to multiply that by either 1 foot over 12 inches or 12 inches over 1 foot. We want the feet to cancel out because we're trying to get an answer in inches. And so we're going to multiply this by 12 inches over 1 foot. Okay. And we get the thing to happen that we want. The units we're trying to get rid of go away. And so you end up doing what we knew intuitively you have to do. Take that 3.5 feet and just multiply it by 12, and that gives you the number of inches. So what is that, 42? If we had multiplied 3.5 feet by the fraction 1 foot over 12 inches, we'd get crazy units because the feet wouldn't cancel. We'd get units of feet squared over inches. We'd still have an answer that was equivalent to our first answer. It just wouldn't be in the units we want. Like you could use units of feet squared over inches as your length units, but just no one does that. We don't want to do that. Okay. Okay, so what about units like meters per second, where you have combinations of these units? So let's say that we want to go from let's say we want to convert 9.81 meters per second squared. This will come up again later, but this is the SI units for acceleration. And 9.81 meters per second squared is the acceleration of an object in free fall at near the surface of the Earth. So we want to convert this to units of feet per minute squared. Using the fact that 1 foot, no, meters, 1 meter is equal to 3.281 feet, and 1 minute is 60 seconds. So we have 9.81 meters per second squared. I'm going to write this as seconds times seconds. Okay, so we're going to start with that. And we're going to multiply it by either 1 meter over 3.281 feet or the reciprocal of that to cancel the meters so that our length is in feet now. So, well, the meters are in the numerator, so we want the meters of our conversion factor to be in the denominator. So I'm going to multiply this by 3.281 feet over 1 meter. Okay. And if we just keep up with what we're canceling, now we don't have units of length in meters, we have it in feet. That's what we want. But our units of time are in seconds. Okay. So now we need to cancel these seconds. And we have it twice, so we have to do it twice. Our seconds are both in the denominator. So we want to have our conversion factor seconds in the numerator. So we'll multiply by 60 seconds over 1 minute. And that cancels one of these seconds. You're just doing this math as if those are algebraic variables, as if they're x or y or whatever. But we still have this other second left, so we have to do it one more time. So multiply by 60 seconds over 1 minute. And that cancels the other seconds. And so now our units are right. We have units of length in feet, units of time in minutes. Multiply that all out. You know, all you're doing now is just multiplying out all those numbers. And you get an answer of 115,872 feet per minute squared. Yep. No, I'm not. In this class, just keep some decimals, whatever feels right to you. I don't have to worry about that because the chemistry people are going to worry about it so much. I'm going to save the time. And the way I happen to write this, you don't have to do this. And if you have a way of converting units that you think about it differently than this, as long as it works, that's fine. This is just a way that works. But I tend to write this as 9.81 meters. And there's the fraction bar. And then on the bottom, I have seconds times seconds. And then instead of parentheses, just to save pen strokes, I just have vertical lines. So then it'll be 3.281 feet, 1 meter on the bottom line, 60 seconds over 1 minute line, 60 seconds over 1 minute. The cancellations all work out the same. It's just, I don't know, to me it's a little easier to visualize, but it comes out the same. Okay. And then we're going to use unit prefixes pretty often. So the ones that we're going to use the most are nano, which you can think of as meaning times 10 to the minus 9th. Micro, you can think of as meaning times 10 to the minus 6. Milli means times 10 to the minus 3rd. Centi means times 10 to the minus 2. Kilo means times 10 to the positive 3rd. Mega means times 10 to the 6th. And giga means times 10 to the 9th. Okay, so that's from smallest to biggest. If you have 5 nanometers, that's a tiny distance. If you have 10 gigameters, that's a huge distance. Or 5, whatever the number was I used. So if you have to go back and forth between things with prefixes, let's say express $50 microseconds. I guess so I didn't give these abbreviations, but nano is represented with a lowercase n. Micro is represented with a Greek letter mu. Milli is a lowercase m. Centi is a lowercase c. Kilo is a lowercase k. Mega is an uppercase m. And giga is a uppercase G. Okay, so say we want to express 50 microseconds, keep it like this, express 50 microseconds in units of gigaseconds. I don't think I've ever seen that unit, but it's a thing. Okay, so how would you do this? Well, there's 2 steps. First, we want to get rid of the prefix micro, the mu, and then we want to add the unit giga. So the first step is, so how do we get rid of, how do we express 50 microseconds just in seconds? Well, since micro means times 10 to the minus 6, you can just replace the micro with, so 50 microseconds. This micro just means times 10 to the minus 6. So this is equal to 50 times 10 to the minus 6 seconds. So getting rid of the prefix is easy. And now we have to add a new prefix. So the second step is we're going to use the fact that 1 gigasecond is equal to 1 times 10 to the 9th seconds, right? Because that's what giga means. We're going to start with our current value of 50 times 10 to the minus 6 seconds. And now we're going to do a unit conversion where 1 times 10 to the 9th seconds is equal to 1 gigasecond. The units of seconds cancel. And now you're just using the exponent rule. So 50 times 10 to the minus 6 divided by 10 to the 9th is 50 times 10 to an exponent of minus 6 minus 9 times 10 to the minus 15 gigaseconds. And then this is kind of an ugly hybrid between a standard number and a scientific notation number. For scientific notation, we just want one leading value before the decimal point. So this is equal to 5.0. If you're going to make the first half magnitude smaller, you have to make the second half magnitude bigger. So this is 5.0